we have to arrange the compounds 1, 2, 3 according to increasing CN bond length. So, this is cyclohexylamine, this is aniline and this is acetamide. So, we have 3 different compounds, and the cyclohexylamine we have a sp3 hybridized carbon atom. So, there is no resonance possible in this particular case. In other words, this carbon nitrogen bond will always remain like a single bond, and this is going to be the longest one. So, this is going to have the longest length. Now, we have to find out between aniline and acetamide which is going to have the next longest bond length. So, here if we compare, this is a sp2 hybridized carbon atom, this again is a sp2 hybridized carbon atom, and this again is a sp2 hybridized carbon atom. We have 3 sp2 hybridized carbon atom here, and when we come to acetamide, this carbon is a sp2 hybridized carbon, and we have oxygen which is also similar to sp2 hybridization. So, that means this is only a sp3 hybridized carbon atom. So, that means there is a little bit difference in the case of acetamide, but otherwise if we look from the nitrogen and carbon, in both the cases we have carbon which is sp2 hybridized and nitrogen which are connected to each other, and in one case we have a sp2 carbon in the case of aniline, and in the case of acetamide we have a oxygen, sp2 hybridized oxygen. So, whether these two change, this small change, does it have any effect on the bond length? We are going to see now. So, if we take the case of aniline, we can draw various resonance structures as shown here. As you are already aware, a carbon having a negative charge is not the most preferred structure for the resonance. Although we can draw various resonance structures, here the nitrogen is also having a positive charge. So, there are couple of negative things which are not acceptable according to our resonance rules. Although we can draw various resonance structures, these structures do not contribute much to the actual resonance form of aniline. So, in other words, although there is maybe some 5% or 10% of these kind of resonance structures possible where there is a nitrogen carbon double bond. So, this is what is the major thing. When there is a resonance happening here, we are getting a carbon nitrogen double bond. So, that means approximately to some extent this single bond and the double bond is going to exist. In other words, what we can say is the bond length is going to be shorter because of this resonance in the case of aniline. But if we take the case of acetamide, what happens here is, here again the lone pair on the nitrogen is shifted between carbon and nitrogen. Now, the oxygen is pulling the electron towards itself. So, here again we have a charged structure. So, oxygen having a negative charge, nitrogen having a positive charge. So, between oxygen and nitrogen, oxygen is more electronegative. So, this having a negative charge is a acceptable structure, and of course, the nitrogen can also be stabilized by electropositive nature. So, in other words, nitrogen can actually have positive charge for some time compared to oxygen. So, that means this structure is actually a possible resonance structure for acetamide. In fact, experimental evidence actually shows that the carbon nitrogen bond in acetamide is neither a pure single bond nor a double bond, but the bond order was found to be 1.5. So, in other words, what we can say is this particular CN bond, this bond remains half the time as a single bond and half the time as a double bond. So, that is how we can say the bond order to be 1.5. So, that means in this particular case we have more of a double bond character. In other words, the length is going to be much shorter compared to aniline, because in the case of aniline these resonance contributions are not very high. In other words, this double bond contribution is much less and the single bond contribution is more. So, that is the reason this may have some partial double bond character, but in the case of acetamide we have more number of double bond character on this C and N. So, that is the reason this is going to have much shorter bond length. And let us look at whether our observation is correct or not. So, in fact, the experimentally calculated bond length for cyclohexylamine is 1.47 angstrom. So, that we know this is going to have the longest bond length that is actually seen here, but it is followed by aniline, because as we have seen through the resonance structures, aniline has more of a single bond and less of a double bond between C N bond. So, that means aniline is having the intermediate bond length. And when we come to acetamide, which has more of a double bond, that is the C N bond is more having a double bond character compared to single bond. So, that is the reason the bond length was found to be 1.36 angstrom. So, the resonance can actually explain the observed bond length of various compounds. And here again we have another example. Here we have to arrange the compounds 1, 2, 3 according to increasing acidity. So, what we have actually seen, that is oxygen is having lone pair of electrons. In all the three cases, we have one is a ortho isomer, another one is a meta isomer, the third one is a para isomer. So, which one can actually give more resonance structures, actually going to give the more increased acidity for this particular proton. So, we are going to actually remove the phenolic proton. So, which is more acidic can be explained based on resonance forms. In the case of ortho, the lone pair of electron is shifted between this oxygen and carbon, and this double bond is shifted towards this carbon and hydrogen bond, and oxygen being more electronegative pulls the electron towards itself. So, we can draw a resonance structure as shown here for ortho nitrophenol. In this particular case, one of the oxygen is having a positive charge. So, this we have to keep in mind. And in the case of second one, what actually happens is, even if the bond is shifted from this particular lone pair, so we can actually draw as given here. This lone pair of electron cannot actually come into the picture of this aromatic ring. So, what actually happens is only the one of the double bond can be shifted as shown here. This lone pair of electron cannot participate in this particular extended conjugation in this particular resonance structure. So, this carbon becomes carbon positive. So, this is actually, as we know, is not a preferred one, because this leads to 6 electron for this particular carbon. And that is the reason this is a less contributing structure for the resonance. And of course, oxygen is having, both oxygens are having negative charge, which is an acceptable resonance form, but carbon having a plus charge is not really favored. So, that is the reason this particular contribution, resonance contribution for metanitrophenol is very less. This is comparatively okay, because here oxygen can have a plus charge, whereas both the oxygen in the nitro group are having negative charge. So, this is somewhat acceptable, because we can actually draw some resonance structures for this particular compound. And when we move on to the para position, actually the para position here, the electron, when this particular, if we start from the bottom one, so how the electrons are actually moving. So, if there is a nitrogen which is actually pulling this electron towards itself, that is actually the oxygen which is pulling the electron from the nitro group. So, this double bond will be shifted towards the carbon and nitrogen. So, this carbon will eventually become a positive charge, but this is quite unstable. So, what happens, this double bond pi electron shift here, and what we end up is a carbocation here. But in this particular case, oxygen is actually having 2 lone pairs. So, this is actually electron rich. So, this donates the electron towards this particular carbon. So, oxygen having a positive charge. So, now you can actually ask the question, sir, oxygen is more electronegative of all the atoms. So, why it should actually donate the electrons? Because oxygen is actually here electron rich. So, this actually has 2 lone pairs, and another oxygen only at the other terminal is pulling the electron. So, literally speaking, one oxygen is donating electron towards another oxygen. So, that is perfectly fine, because there is no electronegativity difference between this oxygen and this oxygen. So, literally speaking, this 2 electrons from one of the end of this nitrophenol is moving from one terminus to another terminal, that is through the pi system. So, the involvement of pi system is very important. This is what we say extension of conjugation when we talked earlier also. So, due to which there is all the resonance structures are possible in this para-nitrophenol, and that is the reason if you look at the observed phenomena, para-nitrophenol is having more acidity. Why we talk about acidity? Because if the oxygen is having a plus charge, this oxygen can actually connected to hydrogen. So, this hydrogen can actually go out as a proton. So, that is what is easily possible. Now, this lone pair of this bonding electron will come to oxygen. Now, we end up with oxygen with no charge. So, that is what is actually the driving force for the acidity, or in other words the proton, the hydrogen can be easily lost in this para-nitrophenol. So, that is the reason para-nitrophenol is having more acidity followed by orthonitrophenol, and there is no resonance structure possible for the metanitrophenol. So, this is having the least acidity. So, resonance forms can actually explain the observed acidity of various nitrophenols. And there are other cases where the lone pair or the bond to bond or the bond to lone pair shift of electrons are given here. So, these are some of the various resonance forms. When there is a carbocation, this is electron deficient, oxygen is having lone pair. So, this can actually donate the electron between these two, and oxygen can actually for some time can have a positive charge because still it has one lone pair. So, oxygen can have plus charge. Now, this carbocation is stabilized here because the carbocation no longer has a positive charge. So, the lone pair actually can donate electron to this carbocation. So, this is one type of arrangement which is possible. That means a carbocation can be stabilized by even the most electronegative atom. That is, this resonance form actually helps in stabilization of this particular intermediate. So, resonance helps in the stabilization, and when we have a allyl like system here as shown, so the double bond, that is simply the pi bond, that is bond to bond electron shift is also possible, which actually gives the carbocation on this particular carbon. So, there is a shift from 1 to 3. So, from the first position carbocation, we end up with the third position carbocation. So, there is a bond to bond shift is possible. Here again we can actually move the electron because here we have more pi electrons, electron density is more. So, this double bond can actually donate electrons to the electron deficient carbon atom. And there is also another case where we can actually move the bond to a lone pair. So, the oxygen can actually pull this carbonyl double bond, C double bond O. This pi bond electron can be pulled by the electronegative oxygen. So, that is also possible. So, these are various resonance forms which can be drawn to show the stability of various species. So, that means here we have a neutral compound getting converted to a charged species or anion. Here we have a carbocation in the starting structure, we end up with another carbocation in the final structures. So, there is no change in the charges. Here again we have a carbocation and oxonium ion is also present here. So, that means there is no change in the charge in this system also, but only in the third system we move from the neutral to an anion. So, resonance can be used to explain various types of electron movement. We cannot separate the plus M effect and minus I effects operating simultaneously. What we observe is actually the resultant of both the effects. In such cases, M, both plus and minus effect will be more powerful since it is the interaction of lone pair or non-bonded electrons, because the electrons are not involved in the bond formation, so they are free to move around. But in the case of inductive effect, it has to operate through the connecting bond, and so it is very weak. This is the reason why the M effect dominates over I effect when both operate simultaneously. And if we go back to the mesomeric effect which we have seen earlier, acid chlorides, esters, acids, amides, carboxylate all can form various resonance structures as shown here. In many of these cases, the most electronegative system, that is halogen here, oxygen in these two cases, or nitrogen, all can have a positive charge because they all have lone pairs, and the formation of a double bond actually gives more stability, and that is one of the reason we can actually draw various resonance structures. And during all these cases, oxygen, the most electronegative element, actually becomes even more by having a negative charge on this. So that is the reason this flow of electron, that is donating the lone pair from either halogen, oxygen or nitrogen, are possible, and this is what is basically due to the mesomeric effect. And here we have two types of mesomeric effect. We will look at the plus M effect in the beginning. So that means donation from the group. So electron donating mesomeric effect from oxygen is shown here, nitrogen and chlorine. This is what we have seen in the previous case where oxygen was not there, because in the previous case we had seen a carbonyl group which is present in all the cases, but here there is no carbonyl group, we only have a double bond. So in this case also the lone pair from the oxygen, nitrogen or halogen can be shifted towards one of the carbon atoms. So these groups are called plus M effect groups or electron donating groups through lone pairs. We also have electron withdrawing groups, that is minus M group. So in this particular case the oxygen actually pulls the electron towards itself because it is more electronegative. So some of the examples include aldehydes, ketones, acid chlorides, esters, anhydride, acids. So all these things whatever we have seen earlier all belongs to the minus M or the electron withdrawing nature of the pi electron compounds. Here we compare the different effect by the same group or atom. Say for example, if we take fluorine, fluorine can actually show inductive effect as well as resonance effect. So fluorine is minus I, that means it actually pulls the electron towards itself by the inductive effect, whereas it donates the lone pair through the plus R effect. That means it can actually donate electron through the resonance contribution, but fluorine can actually withdraw electron through the minus I effect. That depends on what is the adjacent group that is present. If that is a simple carbon atom, then actually the fluorine pulls the electron, that means the inductive effect is operational more. But if it is a carbocation, carbocation is electron deficient. So to stabilize this carbocation, actually instead of pulling the electron, the fluorine actually donates the electron to the electron deficient carbon, so it behaves like a plus R groups. And if you look at the carbon, the methyl groups, they are basically electron donating only. And when we look at the amino group, if it is attached to the carbon, this actually pulls the electron towards itself because nitrogen is electronegative, so this actually pulls the electron. But if it is attached to the carbocation, then the nitrogen can actually donate electron to the carbocation through plus R effect. The same is applicable in the case of carbonyl group. If we simply look at the carbonyl group, carbonyl is electron withdrawing, that is minus I effect, and carbonyl is also resonance. Through resonance also it can withdraw the electron towards oxygen. So these are some of the ways by which we can actually explain how a particular group can either pull the electron or donate the electrons depending on what is the other groups that are present. Let us briefly compare induction and conjugation. The induction is actually found in sigma bonds, that is what we have seen. The sigma framework is very crucial for induction, whereas conjugation is mainly through the pi bonds. In the case of induction, distance matters, that is what we have seen. Alpha groups contribute more compared to beta and gamma, whereas in the case of conjugation, distance does not matter because we have extension of conjugation. So that means it can actually go beyond a few bonds. And induction is enhanced by the electronegativity, but conjugation also is enhanced by electronegativity of the groups involved. Same atom can show opposite effect depending on the charges. And for conjugation, what we require is coplanarity. So this is the comparison between induction and conjugation. And let us look at some of the applications of conjugation. So this is the inherent thermodynamic stability associated with conjugation leads to more stable structures. depending on whether the conjugation stabilizes the reactant or the product, the reaction may or may not proceed efficiently. So, if basically if the reactant are actually stabilized by conjugation, then the reaction will not proceed. If the products are stabilized by conjugation, then the reaction may proceed efficiently. And the equilibrium is favored towards the more stable conjugated species. So, these are some of the applications of conjugation. And let us look at some important thing, color and conjugation. Now, many people have this question in their mind, does conjugation is essential for color? That means we have seen some of the colored compounds like chlorophyll, if you look at, it is green in color, heme is red in color. So, these compounds have extension of conjugation due to which we have the color. So, does it mean that conjugation is very essential for showing the color? Maybe for these kind of compounds we can say yes, but there are many compounds which also show color, but they do not have conjugation. Some examples include gemstones, say ruby, garnet, emerald, all are colored because of the crystal defect, they are colored, but not because of conjugation. So, that means there is some relation between color and conjugation, but not always. If electronic transition actually occurs in the visible region, then the compound is colored. See, for colors to be seen, we need three components. Basically, the molecule is required, I and light. Unless light falls on a substance, we cannot actually see the color of the compound. Say, for example, if you are sitting in a dark room, you can never see the color. What is the color that is present in that entire room? So, that means light is an important contributor to see the colors by human eyes. And how does this actually affect the actual color of the compound? Basically, retinol is essential for our vision. So, this compound actually absorbs the energy, then it shows a violet color, but it appears in the yellow color because this is due to the complementarity of the colors. So, what color is absorbed, opposite of that color is actually shown. So, that is how we see the yellow color. And resonance can also be applied for explaining the acidity of alpha hydrogen due to in the case of conjugate bases. Say, for example, we have a aldehyde, we have a ketone, we have a nitro group, we have a cyanide. So, these hydrogens are having different acidity because of resonance conjugation from the aldehyde group, carbonyl group, nitro group and cyano groups. So, this can be explained by resonance. And acidity of benzoic acids are more than aliphatic acid. This also because benzoic acid can have more resonance structures. In other words, when the proton is lost, those contributing structures, the carboxylate acid is resonance stabilized, that leads to more acidity for benzoic acid compared to aliphatic acid. And the basicity of aliphatic amine or especially the plus I effect are more than the aromatic amine. This also is an example of resonance. Actually, the mesomeric effect is profound when it is attached to multiple bonds, say pi systems or aromatic systems. Basicity is due to the ready availability of electrons for protonation. In aliphatic compounds, there is no resonance, so the electrons are readily available for protonation. In aromatic systems, the lone pair of electrons will delocalize into the aromatic ring. So, the electrons are not readily available for protonation. This makes them less basic than the aliphatic systems. Now, the next question is, can the same moiety show different effects? That means formal structures. Say, for example, if we take an oxygen carbon bond, that means this is very similar to an ether, vinylic ether type system. So, can it show different plus and resonance effect? If you look at this structure, the oxygen is electronegative. So, this actually pulls the electron towards itself through the minus I effect, but the same oxygen can actually donate electron towards plus R or plus M effect. So, the same group can actually show different types of effects. See, this is another term which many times people get confused, mesomeric versus electromeric effect. Of course, this electromeric effect is no longer being used in the standard textbooks. So, what is the difference between these two is mesomeric effect is basically the polarization of a group conjugated with a bond either plus M or minus M. This operates only when the group is directly connected to an unsaturated system. So, the resonance is possible only if it is attached to the conjugated system or unsaturated system directly, then only the mesomeric effect actually happens. And in the case of electromeric effect, it is actually an intramolecular movement of electrons from a pi bond to another atom in the molecule due to the attack by a reagent. So, that means this does not happen normally unless an external group comes and attacks the molecule. After another species, either nucleophile or an electrophile, attacks a pi system, how the electrons are moving, that is what is explained by the electromeric effect.